Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Every year, the world produces over 140 billion metric tons of agricultural biomass waste, stalks, husks, leaves, and straw. What do we do with most of it? We burn it or we let it rot. In doing so, we release millions of tons of black carbon and methane into the atmosphere. At the exact same time, humanity has an insatiable addiction to building. Concrete is the second most consumed substance on Earth after water. But to make Portland cement, the glue that holds concrete together, we have to bake limestone at nearly 1,500 degrees Celsius. This single industrial process is responsible for a staggering 8% of all global CO2 emissions. We have a massive waste problem and a massive emissions problem. But what if one could solve the other? Welcome to the fascinating world of agricultural waste engineering, where material scientists are turning dead crop residues into high-performance industrial building materials. Using crops for construction isn't a new idea. In fact, it's one of the oldest engineering tricks in the book. Over 3,000 years ago, ancient Egyptians recognized a fundamental principle of composite engineering. Mud on its own is brittle. It cracks under pressure. But when they mixed in leftover straw from the wheat harvest, the flexible plant fibers acted like microscopic rebar, absorbing tensile stress. The Ming Dynasty took this a step further, using a mixture of slaked lime and sticky rice soup to bind the bricks of the Great Wall of China, creating a mortar so strong that centuries later, bulldozers still struggle to break it apart. History knew the secret. But modern engineers aren't just making mud huts. By combining advanced chemistry with agricultural waste, they are engineering materials that rival, and sometimes beat, conventional steel, concrete, and timber. Let's look at the world's most popular crop, rice. Globally, we mill about 500 million tons of rice every year. This leaves behind 100 million tons of rice husks. The husk is tough, abrasive, and practically indigestible for animals. It's a waste nightmare. But if you look at a rice husk at the molecular level, it contains a hidden superpower. Up to 25% of the husk is made of silica, the exact same mineral found in quartz and sand. When engineers burn rice husks under highly controlled temperatures, specifically between 500 and 700 degrees Celsius, the organic matter burns off, leaving behind a highly reactive, amorphous material called rice husk ash, or RHA. RHA is what engineers call a pozzolan. When you mix ordinary cement with water, a byproduct called calcium hydroxide is formed. It's a weak, soluble compound that doesn't add any strength to the concrete. But when you add rice husk ash, its amorphous silica reacts with that useless calcium hydroxide, triggering a secondary chemical reaction. By replacing 15 to 20% of traditional Portland cement with rice husk ash, engineers actually increase the compressive strength of the concrete while dramatically lowering its permeability to water and road salts. We get stronger, longer-lasting bridges and buildings while cutting cement emissions by a fifth. It's not just concrete. The timber industry relies heavily on engineered woods like OSB and particle board to build the walls and floors of our homes. But doing so requires cutting down decades-old trees, chipping them up, and gluing them back together with toxic, formaldehyde-based resins. Wheat is grown on more land area than any other commercial crop, leaving behind massive amounts of golden stalks. Companies like CalPlant in California have developed industrial processes to turn this agricultural waste into medium-density fiberboard, MDF, that performs exactly like wood. But how do you glue it without toxic chemicals? You don't have to. The plant already did it for you. Plant stalks contain a natural polymer called lignin. It's what makes plants stand upright. Using intense heat and extreme mechanical pressure, engineers can actually melt the natural lignin inside the wheat straw. The lignin acts as a bioadhesive, binding the fibers together into dense, rigid panels. Because these straw boards are compressed to such high densities, there is almost no oxygen left inside them. As a result, they offer superior acoustic insulation and are heavily fire-resistant compared to traditional timber. And the best part, while a pine tree takes 20 years to grow, wheat grows back every single year. But perhaps the most futuristic leap involves recruiting biology to do the manufacturing for us. Engineers are now taking coarse agricultural waste and inoculating it with mycelium, the root structure of mushrooms. The waste acts as food and scaffolding. The mycelium aggressively grows through the waste, digesting it and knitting the loose particles into a solid, lightweight mass. After a few days, the material is baked in an oven to kill the fungus and stop the growth. The result is a biocomposite material that is pound for pound stronger than concrete in tension, entirely fire-resistant, highly insulative, and 100% biodegradable at the end of its lifespan. It is currently being used as high-end architectural acoustic paneling and eco-friendly insulation. For the last 2 centuries, our paradigm has been linear: extract, process, build, and discard. Agricultural waste engineering represents a shift to a circular economy. We are finally learning to build our cities the way nature builds forests, using waste as a foundation. We don't need to dig deeper holes in the ground to find the materials for the future. The materials are already here, growing right in front of us, waiting for the right engineering to bring them to life. If you want to learn more about the incredible ways engineering is shaping our future, make sure to hit subscribe. Thanks for watching, and I'll see you in the next one.